Okay, I think it's time to start. Welcome back, everyone, for our second series of Ethical and Responsible AI seminar series. We successfully organized it last spring with a line of speakers within Mehari and outside also. This year also, we have invited many expert researchers from the other universities as well as researchers within Mehari and from our school. I would go with a brief introduction for our for today's speaker, Dr. Graham West. Dr. Graham West is an assistant professor in the Department of Computer Science and Data Science. He started here in July of 2024. His research focuses on applying machine learning methods in the digital humanities, and his doctoral dissertation is on fitting the morphology of simulations of interacting galaxies to synthetic data, focused on developing optimization methods to model and fit simulations of interacting galaxies to synthetic and observational data. After graduating magna cum laude, Dr. West joined the Ancient Lives Project, a team of data scientists and humanities scholars aiming to bring advances in machine learning to ancient Greek papyrology. Specifically, his work has consisted of developing deep learning methods to perform handwritten text recognition and dating of papyrus fragments. As a data science educator who is passionate about both the field and his students, Dr. West's objective is to equip students with the skills, knowledge, and experience they require to succeed in the evolving landscape of data science. So before giving the stage to Dr. West for the wonderful presentation today, I would say there is a small, the talk will be until 1 p.m. and then we will take all your questions. Feel free to post your questions on the chat so that we can take from the chat, and also you can unmute yourself and ask questions directly. There will be a post feedback survey for this session. So that will be posted on the chat, which you can fill up after this session and provide us feedback to improve these seminar series in the future. So thank you very much, everyone, to find time to attend this seminar series. And Dr. West, the stage is yours.
Cool. Can y'all all hear me very well?
Yes.
Cool. And y'all can see my screen here?
Yes, we can see your screen.
Awesome. Well, thank you, Dr. Gupta, for inviting me to be a speaker in the seminar series. So today I'd like to talk to you about me and my group's research over the past few years on bringing advances in AI and ML into ancient Greek papyrology. We have a group that kind of spans from Meharry, University of Kentucky, and Middle Tennessee State University. And also Matt here, he actually just started working at Argonne National Lab, so our group is kind of expanding a little bit. It's kind of cool. Um, so if anybody has any inquiries about the project or wants to become involved or anything, feel free to email me on that email address there after the seminar. But for our outline, I thought I'd talk about kind of the introduction to our kind of problem statement here, as well as the main data set that we have access to, that we've used to develop all these models. Then we'll talk about how we use that data set to train models that perform manuscript transcription, and then paleographic dating, also synthetic character image generation, our recent work on natural language processing, and also our vision for the future of AI-assisted digital humanities. So let's start with the basics here. About 100 years ago, a group of archaeologists from Oxford's Egyptian Exploration Society discovered a large collection of papyri in a dump site in the ancient Egyptian city of Oxyrhynchus. About 500,000 papyrus fragments were found there, and most of them were ancient Greek, some in Coptic, some in Latin, and so on. But in the past 100 years, only about 15% have actually been transcribed by expert paleographers and papyrologists. So the work is slow. There's not very many people in who are trained to do this work where they can actually read these ancient languages and then transcribe what they see on the fragment. So A number of years ago, the Ancient Lives project was created as an international collaboration between humanists and computer scientists, and its goal was to create a crowdsourced data set that annotated character images, or essentially character locations and labels from images of these Oxyrhynchus papyri. So essentially, volunteers could go onto a website and then kind of click on the location of characters they saw and then label them. We'll see more about that in a minute. Anyway, the project acquired several million annotations across about 12,000 different manuscript images, and subsequently the datasets ALPub and ALAll were produced. ALPub is actually available on Kaggle. It consists of cropped images of individual Greek characters from published manuscripts from this Oxyrhynchus collection. ALAll contains that plus some unpublished ones that only we have access to because, they haven't published, so we get them, but the rest of the world doesn't. Anyway, if y'all are interested, y'all are welcome to look up ALPub on Kaggle. I think Matt put that there. So, um, when it comes to thinking about, cropped images of characters and so on, obviously one of the first things we might think of is like a data set like MNIST, kind of these standard little toy data set for training simple CNNs and such and Keras and so on. But what we work on is certainly a lot more complex and noisy than that. And it's actually even worse than the image on the right, which is just a Byzantine era book or a codex. Now, what we have is pieces of papyrus that have been buried in the dirt in a dump site for 2,000 years. So there is a lot of damage. There are a lot of holes. There's a lot of tears. There's a lot of gaps. There's faded ink. Some of the cases you have basically there's only ink clinging to fibers left. Basically, this one on the right is just hideous. There's almost no the almost all the actual papyrus left is just that which the ink is connected to. So you can see that there's characters that get kind of sliced down the middle, like this one here. That can be annoying. There's characters that have like a hole in the middle of them, like this one here, right? So this is not just, a simple MNIST problem where all the characters are nice and pristine and cropped and so on. It's quite a hard problem. So I mentioned how ALAll was a crowdsourced data set. So volunteers, expert or non-expert, could go onto a web interface that was developed and essentially click on the locations of characters and then say what character it was. And then a cropping algorithm was developed in order to kind of snip out and crop out individual characters. And from that data set, or from that process there, this data set was created. So we have the number of characters of each of the 24 Greek characters from alpha to zeta, or I should say from alpha to omega if we're doing Greek alphabetical order. We can see the number of samples in the ALAll dataset and the ALPub dataset. So as you can see, there's quite a range. There's some characters that are used much more frequently, like alpha, 42,000 in ALAll, versus psi with 900 examples. So it's definitely an imbalanced classification problem. So that's, challenging. And on the right here, we have some examples of some of the better looking ones that were cropped. So you can kind of see what each of these characters looks like. I mean, it's worth noting though that each character has multiple ways of writing it. You're familiar with like say uppercase and lowercase. Um, those distinctions don't really hold in ancient Greek, but for the most part, that kind of understanding will work. There are multiple ways of writing the same character. So just because we see a character right here, that doesn't mean that that is the only or even the most common way that that character might be actually be written. Okay, so now that we've talked about the data set and the images, let's talk about some of the AI ML models that we've developed. So first up is perhaps just the most important and most kind of straightforward and as well the kind of barrier to entry for the rest of the models, simple handwritten text recognition, so HTR, essentially reading and transcribing the manuscript with AI. So there's three steps to this. There's character detection with a YOLO model, character classification with a ResNet model, and then line sequencing with a mean shift clustering method. So, um, for character detection, basically detection just consists of identifying and cropping out objects of interest in an image. So, on the left here, we have the ability to, kind of a simple yellow example showing how we have an image where some people and a bus and so on were detected in an image. For us, what we'll have is essentially characters that are in an image. So YOLO is a pre-trained PyTorch model. So we basically transfer learned that to detect characters. And if you're wondering why this image on the right is stretched, it's because YOLO has a fixed horizontal width and vertical height for their images. So it was resized. So here's a little bit of just some training metrics. So the validation, precision, recall were 88 and 84% for this YOLO model, which is actually pretty good because it's in, the data set, like I said, is incredibly noisy, um, and it's just it's a beast to try to model. So we're happy with the 80s. The next model is actually a bit better even. But so here's an example of seeing what YOLO looks like when it's found characters. So if I can zoom in here, um, so you can see basically it was able to find most of these characters. This is actually a very good example of a fragment where there's not terribly many tears and holes in throughout. One thing to notice, you can see there's these kind of larger boxes and such. That's because since YOLO has a finite um, size of image it can be inputted that it can receive as input. Essentially, what we did was to perform YOLO and detection on a larger image. Just essentially um, perform a sort of sliding window technique where the you essentially crop out 640 by 640 pixel sub images of the real image and basically do YOLO on all of those, and then handle overlaps and duplicates and so on. But basically, each of these boxes here kind of shows the non-overlapping areas of those kind of sliding windows, and that's how we were able to get the whole thing. Fairly simple. So that's detection. Next is classification. After you've cropped out these characters and you have these little images of those, how do you tell what character it is? So for that, we used a ResNet. And in this case, we actually got a validation accuracy of 94%. So this actually did even better than the last model. And here is essentially what it looks like if you combine these. So on the top left here, we have YOLO cropping out that delta, and then ResNet predicting it with 100% accuracy. I should say 100% accuracy, 100% probability, excuse me. So it was very confident about that one. Um, cool, so that's what happens if you combine detection and classification. The next step is once you have essentially detected and classified all these characters, you then want to put them in a line so that you can essentially, display it in a sort of Unicode format, and it just be essentially a copy of what you see on the fragment. So this was actually a pretty hard problem because there's, like I said, there's just a lot of noise with YOLO. It can sometimes find false positives or duplicates of characters. Basically, it can find basically kind of overlapping images of the same character. Again, it's just because there's just so much noise with these images because there's so much damage and such. Anyway, we chose to use mean shift clustering because it is robust to the it can handle a variable number of clusters. And basically, what you would kind of give it is something that is related to the distance between clusters. So we can estimate roughly what the number of lines is. Even if we can't tell exactly, it's not too hard to kind of get a rough estimate of the number of lines and then the distance between lines, and then you use mean shift with that bandwidth, and then you can get a pretty good estimate of what the lines ought to be. And also, one of the things that makes this difficult is that this particular image doesn't kind of indicate it as well as others, but what can sometimes happen is that different portions of the fragment, due to tears, can actually be angled slightly differently. So you can see that this part on the top is a bit more horizontal with the line here, but on the bottom it's kind of slanting down to the left here a bit more. So that can be problematic for trying to detect these lines. So we have to essentially do a sort of a local rotation correction by minimizing the histogram, the Y histogram entropy of the location of these characters, so that we can actually determine, what actually belongs on the same line. So, excuse me. So this problem was actually rather difficult, but once you've solved that, you can then just sort things by Y and X, and then you have your lines. So, if we take that fragment and do detection and classification and line sequencing, um, we can obviously just create a simple Unicode text file, but also just kind of for fun. we have a fun little kind of rendering of the document here by kind of placing all the characters in the locations that you'll have found them. So on the right here, we essentially have a sort of a digital reproduction of what's on the left. You can see some examples where it didn't quite work. Or say right here we have the row alpha new. So I'm going to read that yellow. We have a row alpha, and then it sees a lambda, and that's because basically it detected this guy, but did not detect this guy because of that split, that little line there. That's one of the kind of the challenges with all this damage. So I'll bring this back up a little bit, but this right here, this idea that, as good as our models can be, they'll never be perfect. This will actually lead us into one of the ideas that we'll talk about later on, which will be using natural language processing to actually automatically correct AI-generated transcription errors. Essentially, if we know ancient Greek and we know that this right here isn't a word, but say epsilon, rho, alpha, nu is a word, then perhaps we can train a model to kind of automatically correct that. So we'll come back to that in a little bit. Um, so not only can you actually apply our models to just ancient Greek papyrus, but here's an example of applying YOLO and ResNet to actually a Greek stone inscription. So we have an image of essentially a stone that had a hammer and chisel inscription. YOLO and ResNet were both able to quickly detect and classify these characters. So these models are actually robust to different media. Moreover, just for the heck of it, we tried throwing our YOLO that was only trained on ancient Greek at different languages, just to see, just out of the box, without retraining it on, say, Hebrew or whatever other language, how well would it do? And it actually didn't do too bad. So, which lets us know that, okay, well, if we found a data set for Hebrew or Korean or Sanskrit or whatever other language we'll be interested in, it would actually be pretty easy to retrain YOLO. Obviously, um, even if YOLO works pretty well multilingually, the rest of that won't because alpha is not a character in Hebrew and so on. Anyway, when it comes to then changing the ResNet though, we're interested in, well, do we have to basically retrain the ResNet from scratch every time we want to add a new language? Um, if so, then we need a big data set, but how can we make this work? Well, actually, if we simply just transfer learn, we can actually get away with kind of a small data set. So here's a kind of just a very simple example. As obviously this is a very pristine example. These are kind of perfectly cropped characters with no tears or anything. It was just kind of the most easily accessible data set at the time. But it was essentially a proof of concept to see, hey, we actually can take our data set, our ResNet model that was trained on ancient Greek, and then transfer learn the last couple of layers and make it predict a different language. And still we're trying to give it accuracy. The original model was a 94% validation accuracy, and this one is now 92% validation accuracy. So that actually shows that we really don't need to go back and say, create a whole other crowdsource initiative to get a big data set for Hebrew or Sanskrit or whatever, and then retrain the entire neural network on that. We can actually get away with a small data set and then translating. So that's good news. So there is some of our work on manuscript transcription and handwritten text recognition. Sorry, my throat's starting to die. Let me drink some water here. Excuse me. So let's now look at our work on paleographic dating of manuscripts. So essentially what this means is predicting the time period in which the manuscript was written. So what we've done is develop a cool pipeline that essentially lets you take an input image of an entire fragment, does a whole bunch of deep learning stuff and some feature engineering and so on, and then outputs essentially a distribution of predicted dates. So we'll come back to this in a moment. So when it comes to dating papyri, there's essentially two kinds of papyri. There's documenting papyri, things which have they're like contracts or receipts or government documents, things that usually contain a printed date, and it'll say in the third year of King whoever, right? There's also literary, subliterary, or religious papyri. These things would be like things that have Homer or a gospel or a magical text or some mystical thing. Who knows what. And these usually don't contain dates because people don't really care when so and so scribe copied Homer or the Gospel of Matthew or whatever. So, um, if no date is present, i.e., we're looking at literary fragments, what essentially happens is that paleographers, people who study the ancient writings and how to date them, they have to resort to dating these fragments by looking at the handwriting style, or also called the script style. And this is actually cool because handwriting styles of different languages change somewhat reliably over time. So to date, no large-scale, prior to our work, no large-scale statistical analysis on images of ancient Greek scripts has been performed. But well, we actually have some cool stuff now that we can show here. Now there have been some studies, but not to the extent that we have. So you'll see how big our data set is. So it's actually a new data set, not just the ALL data set. Anyway, so we have this idea that documented papyri have the dates written on them. And also, if no date is present, scholars have to look at the handwriting style. Well, that means that if there is a date, that can and handwriting style does relate to the date that something is written. That means that you can create essentially a relationship between that handwriting style and that time period, that date. So what we wanted to do was create a big pipeline that would essentially, have a big data set that we could train on, and the data set would essentially have a bunch of images of papyri and their known dates, essentially feature engineer those images in some way and feature select, and essentially be able to take advantage of looking at the handwriting style in some way, and then use that to predict the dates. So to do this, we web scraped images and metadata from several online papyrus data sources. Berlin, Florence, and Duke all have kind of massive online papyrus databases. And we essentially we scraped all the metadata, especially the date information, and we also basically filtered out um, anything that was not documentary, aka we only used uh, papyrus fragments that had known dates to train the model. As you can see, this website is in German. The Florence one is in Italian. So, the data wrangling and cleaning was, a nightmare. But, you do what you gotta do. So, when processing this data set, we essentially did two things. We took all the images and ran them through the HTR models. So we put them through YOLO to find the characters on them, and then ResNet to classify them. And that essentially, creates the image side. As far as the date side, we basically reformatted the dates to make sure they all agree because every website used a different format and they all used multiple formats, so that was fun. So at that point, we have the whole data set. And the reason that we chose to do this is because essentially, if you take a fragment from the third century and then you crop out all the characters, well, obviously all those characters are also from the third century because they're from the fragment that was from the third century. So what you can do then is not only do you have this fragment is from this time period and make a mapping between those, that's what you eventually want. But in order to make that, what you can do is essentially make mappings between a character and this time period, and then use that to then create the entire fragment model. So we'll see that in just a minute. So when it comes to the actual data set that we ended up with, on the top here you can see we ended up with a total of 7,000 fragments, and on the bottom here, 778,000 total characters. You can see these columns, they're essentially 2 century windows. Um, as a start for the first phase of this project, we started basically making this into a classification problem where each of the date classes spanned 2 centuries. So essentially, the goal is to kind of predict which of these 2 century wide bins, temporal bins, does the fragment belong into. Obviously, 2 centuries is rather wide and rather generous, and it's not the most useful thing ever. So that was why we started with that and basically tried to kind of get a proof of concept, see if it works. As we'll see, it works, and what we've been doing now is trying to reduce this temporal resolution, and we've done it quite well. So more about that in a minute. Anyway, what you can see though is just like with the AL data set, there is a lot of class imbalance. So if you look for alpha on the total there is 71,000 alphas and only 1,000 size. So same problem. There's just some characters that pop up more than others, and you have imbalance classification problem. So to fix that, obviously, one needs to do a lot of data balancing and data augmentation. So when it comes to the actual pipeline, though, that we have our data set, here's how it works. Essentially, we will provide the entire input image. We will perform HTR on it. We will use YOLO and ResNet to crop out the characters and classify them. What we'll then do is filter out any characters that YOLO and ResNet were not confident on their selection, their choices. Um, YOLO can sometimes find false positives. Say it can find what it thinks is a character, but it's actually say just a hole in the fragment, and there's actually no character there. Um, in that case, you can get rid of those by realizing, hey, there's no ink pixels there. There's not much dark pixels there, so we can throw that out and filter it out. And also a ResNet, it gives you a probability distribution for all the characters that it's trying to predict on. And if it's not very confident in any of them, that lets you know, okay, this one we probably should throw that one away. So after filtering those and kind of keeping only the ones that were, that are kind of the good ones, um, we then group all the characters based on their character type. So basically all the alphas go here, all the betas go here, and all the gammas go here, and so on. And each one of these these groups of characters, all the alphas and so on, each one of them gets their own ResNet that actually will date that character. So each of these ResNets um, was created by transfer learning the original ResNet that was trained on ALL, but retasking it via transfer learning to predict the dates. So basically, the date of the fragment that the character was from, that's the date that the character is from. So that's what the ResNet will try to predict for that. So we'll get the distribution for that. We'll basically get that for every character from each character class for every fragment. Now, having gotten the distribution of dates for each character on the fragment, what we'll then do is aggregate them because there's a variable number of characters. We can have either like 0 alphas or 100 alphas on a single fragment, right? So you need to essentially aggregate those to make sure that you have a constant dimension size for the next phase of your machine learning steps. So we aggregate those with the math you see there, essentially a sort of uh, um, plausible succession and sum of probabilities across different date classes and so on. Um, Once we've done that, we essentially have some more features that we can use to then date the entire fragment. So that last one, the fragment dating model, it essentially takes these features, these aggregated predictions of individual characters, and then the thing it tries to predict is the same thing that the character model is trying to predict. It just tries to predict the date of that fragment. So at that point, that's what it outputs. So just to recap, you give the input image to the HTR models. It crops out the characters, filters out the bad ones, splits all the characters based on their character type. It dates all those, then aggregates them to make them a fixed dimension, and then uses those aggregate dates to predict the date for the entire fragment. So, just and for kind of a naming convention, we use the term character dating models for these ones that date individual characters, and the fragment dating model to refer to this final part that takes these feature engineered things and then predict the date for the whole fragment. And also, by the way, that is just a simple dense network, nothing too complicated there. So, with that in mind, what we have here is some results for the character dating models. They were all trained, with the parameters that you see there. But what we have here is the confusion matrices. So if we zoom in here, we essentially have a confusion matrix for each character, so alpha, beta, and so on. And we have basically the true data distribution on the left, and then the predicted on the right. So honestly, what we would like to see is a strong diagonal. That would mean that we got most of them right. What you'll sometimes see, most of the time actually see, is that uh, the diagonal is less strong on these two here. That's because basically in these two time periods, there was a lot of papyri written. That's when most of the papyri throughout history were written. So there's an incredible amount of variability. So those are the kind of the hardest to predict. Um, so that's one thing. You'll see basically kind of these two diagonals are a little lower than the rest of them. Also, what you'll see is overall the the lower triangle has more probability than the upper triangle. The reason for that is because essentially as um, let's say a character handwriting style is introduced in this time period. Well, just because we went to this next time period doesn't mean that that went away. Basically, new handwriting styles can crop up over time, but the old ones still remain. And at any point, a scribe can choose to adopt an older writing style whenever he wants. So what we'll see is essentially a sort of diffusion where older handwriting styles persist, but less so, and then newer handwriting styles will appear. So because of that, we'll never see a handwriting style that appeared here, appear back here. That doesn't really work, right? So overall, what you'll see is a lower triangle that has more probability than the upper triangle, usually. So that's interesting. Um, Anything else I want to say here? Um, ah, and also one last thing is the validation accuracy for individual characters and their data models was between 35 and 45% depending on individual characters. Now that sounds low, and it is, but realize that this is individual characters. So what can happen is that as you add more characters, a sort of law of large numbers starts taking effect, and you actually get more accuracy as you for your fragment model as you have more characters. Let's think about this. We have five different classes, so the average accuracy we might get just for random chance would be 1/5, so 20%. So we're getting enough above that. We're getting about twice that, right? So 35 to 45%. As you add more and more characters, that will essentially cause a sort of law of large numbers effect to take place, where that kind of boost in accuracy kind of gets multiplied. So as you can see here, we essentially divided the fragments into kind of quartiles based on how many characters are in the fragment. So for fragments that had only a few characters, their prediction for the entire fragment. Again, this is the entire fragment now, not just individual characters. That prediction was only slightly above random chance. But as we get more and more characters, we see it increase quite a bit. We're by once we get to a few hundred characters, we're actually up to the 80% accurate level here. And also, if you look at our confusion matrices for these fragment model, what we'll see is actually a much tighter um, confusion matrix along the diagonal here. So still, this time period right here is where there's the most confusion, but it's much better than the individual characters. So the whole idea is that, dating individual characters is unreliable, but it's reliable enough that if you have many of them, it's sort of law of large numbers, law of large numbers takes place, and you basically can have your accuracy multiplied. So that was the state of our project as of our last publication. What we've been doing since is several things. We've been attempting to increase our temporal resolution. So, like we saw here, the date classes were 2 centuries wide. This was just kind of an older demo I did before, so it's showing 50. But what we've settled on for now is actually a 100 year wide window. So we've essentially doubled. We probably shouldn't actually look at this. It's a bit confusing. We've changed it since then. But instead of doing a 2 century wide window, we're now doing a 1 century wide window. So that's basically 10 classes for 1,000 years as opposed to five. Um, and we've kind of changed how we're kind of depicting all this stuff to kind of show the actual full distribution in time. So though this one is a bit outdated, showing up kind of 50 years, the overall kind of thing, the overall look here is correct for kind of how we've changed. So we have the true date distribution. Basically, this fragment was it was known to have been written uh, in this time period here, and then the green distribution here is essentially the model's guess at when it was written. So I don't have the most up-to-date statistics for you on the slide here, but I can go ahead and tell you that when we've reproduced these same types of results here, instead of doing it in terms of accuracy, we've now started doing it in terms of median, I think it's median absolute error in years between the kind of the overall prediction of the model and the true value. And it turns out when we get to these kind of higher these fragments would have at least like 150 characters. We're actually getting a median absolute error of about 40 years. So we're able to actually able to date fragments on average within about 40 years of their actual date. So that's pretty cool. Um, for comparison, uh, Google Google DeepMind has over the last couple of years developed a project called Ithaca, where they're actually instead of looking at images of papyri, they're looking at the actual text of ancient Greek transcriptions. And they've actually gotten to within about 30 years. Um, the way they're calculating it is a little different than the way that we're calculating it. And also, they have a bit of an advantage since they're using text. Um, a Greek stone inscription will typically, be some sort of a, memento to some king's victory. Like, oh, Caesar won the battle of so and so. And if the inscription says that, well, the battle of so and so happened at that time period. Obviously, the model's going to be able to tell when that's from. So their ability to date that accurately is cool, but it's actually not quite as impressive as it sounds. Since we're doing just images and there's actually no semantic content, nothing, none of our models actually is incorporating like what the text says and what it means. It's just what the text looks like. The fact that we're getting kind of comparable results with that limitation is, in our minds, very impressive. Also, um, the way that we've been able to achieve this improved accuracy, this kind of 40 median absolute error of 40 years, is by actually modifying the pipeline a little bit. So instead of looking at just individual characters, we're also looking at cropped patches of several lines of characters. Um, we have a few colleagues um, from those the Berlin and Florence archives, and they had suggested that there's some things, there's some features on papyri that are essentially inter character and inter line that actually tell when a fragment is from. So essentially, if a stroke from a character kind of goes way below the line, that's actually indicative of essentially the date. So what we did was we kind of took their advice, and included kind of dating based on the individual characters that we saw before, but also dating entire patches there. We kind of treat the patches as a sort of a 25th character. We've also improved feature engineering. And also what we see here is actually something called an inclusion map. Because what we wanted to see is, well, can we actually look and see what the model thinks is important for dating? And then can the trained professional look at this and say, yes, I agree. That thing right there is what I would have used to date the thing, to date the fragment. And it turns out it's actually pretty effective. There's several ways to do this. We're trying to figure out the best one. Right here, we're seeing an inclusion map. There's also things called saliency maps and class activation maps. So we're trying to figure out which one of those is the best. They all have kind of pluses and minuses and so on. But this is also one of the really cool avenues of looking down, trying to kind of have some AI interpretability, so that the paleographers can kind of see what the AI sees and kind of validate it with what they think, and also see perhaps the AI can see things that they can't, and they can learn something and up at the field. So that's cool. So the paleographic dating aspect is one of my favorite parts of our project. It's essentially my baby. I love it. It's a cool project. So another cool thing that we've been working on, worked on a while back, is a synthetic character image generation. So I mentioned how earlier that there's a lot of class imbalance. With alpha having say 40,000 examples and then psi having about 1,000. So one thing that we looked into was using StyleGAN to actually create synthetic images of these low sample count characters. So basically, here's what we have there. Um, on the right here are all of these are completely generated images. None of these are real. The bottom one here is psi, and the top one here is alpha. So if we zoom in here, it's actually um, very hard to tell the difference. We also actually trained all of our models on these new, essentially on a data set that had basically all the original ones, plus synthetic characters, and our performance kind of between the two is pretty much identical. There's not really any significant, unimprovement. I think if I recall, the accuracy for the overall accuracy stayed about the same, while the accuracy for the low sample count characters improved a little bit, which means that other characters actually might have decreased a little bit, but I don't have those numbers for you. But essentially, this actually throwing our synthetically generated characters into our training, it certainly didn't hurt the performance terribly. And it seems like it might have actually improved It did improve the performance for these generated samples characters, but it remains to be seen how much it affected the rest of them. Perhaps the most interesting part of this work was giving essentially testing real papyrologists by showing them images of real characters and these synthetically generated characters and asking them if they could tell the difference. So it's only is it synthetic or is it real? It's a binary classification problem. Their mean accuracy was about 55%. So they only got very slightly above random chance when they were trying to tell, via their own, understanding their own vision of what character was real versus synthetically generated. So since since they're very convincing, essentially, they were excited about various applications of synthetic characters, such as document construction or various types of educational uses for kind of showing students like these are the different ways that psi can look, and here's the ways that alpha can look, and you just kind of have a way to kind of just completely generate new ones, right? So this is an area that has some promise as well. Um, the most recent research avenue that we've undertook is natural language processing. So we're kind of just at the very beginning stages of this. Um, as I said earlier, our AI-generated HTR transcriptions are imperfect. Obviously, the model can get something wrong because YOLO, as you saw from that earlier case, it thought that Ada, sorry, it thought that new was a lambda because there was a bit of a, like a, it was like there was a tear through it and it messed it up. So the model can make mistakes. There's also just gaps and holes in the fragment, and the entire character can just be gone and the models won't have any, the model won't have any idea what character should have gone there, and it also won't detect anything because there's nothing there to detect, right? Also, a scribe can actually just make a typo. Right? That happens. They'll just write the wrong letter. Even if our model correctly guesses the letter, the guy wrote the wrong thing, right? So that's problematic. And also, they can use abbreviations like crazy, especially in documented papyri. So what we've been looking at is trying to use NLP methods to essentially perform a sort of autocorrect, an ancient Greek autocorrect for our AI-generated transcriptions with our HDR models. So essentially, given a knowledge of like a large ancient Greek corpus and ancient Greek language, can we infer the most likely corrected text? So if you have an entire sentence right, but miss one character, it should be pretty easy kind of to correct that one character based on the context of the rest of it, right? So essentially, how well can we push that? So we're looking at a few architectures for that. We're looking at on the simple side, we're looking at LSTMs with attention, but hopefully in the longer term, we're looking at transformers like BERT and so on. So we're trying to start small for now. And to give y'all an idea about how challenging this is, um, so some of the challenges are that obviously there's not a lot of data for ancient languages such as ancient Greek. So obviously ChatGPT, when they train that, they can just web scrape the whole internet, and there's tons of English just out there because English is like just the language that the world speaks pretty much, um, for better or worse, stupid language. But ancient languages, they don't have as big of a as much data about them, so you can't train as big of a model because of that. So that's problematic. Um, Also, ancient languages are really weird because they don't have many of the features that modern languages do. Things like punctuation or spaces or new lines or cases. It's bizarre. There's a reason you need to be an expert in order to read these things. It's not just um, can you read modern Greek? No, it's ancient Greek. It's imagine trying, if you know English, imagine trying to read, Anglo-Saxon from 1,000 years ago. They aren't even close to the same language, right? So, for essentially to try to simulate this and train our models, what we're trying to do is this. So basically, we have a corpus of Greek text from the the TLG dataset, the Thesaurus Lingua Graeca, the Greek thesaurus. It has just a bunch of works by Homer and various things in Greek. Um, and it's all formatted kind of modern like. So our goal is essentially to take that and kind of artificially mangle it so that it looks like ancient Greek. or so, well, a few things. So that it looks like ancient Greek, I remove the spaces, remove the periods, remove the case distinctions, but also now that we've made it look like ancient Greek, which is, those things, um, we also need to, if we're going to try to, train a model that can perform autocorrection, we need an X and a Y. We need our inputs and our outputs. So what we want to do here is essentially take our ancient Greekified corpus of Greek text and essentially artificially degrade it, artificially mangle it, so it looks like it came from a papyrus that has a bunch of holes in it, right? So essentially what we can do is, I have a probability of, going character at a time, removing it, adding a fake character, swapping it to a different character, basically, artificially mess it up, add gaps and so on, and essentially take that just horribly mangled text and then try to recover the original thing that had not been mangled. So that's our approach to creating the model. So obviously, what will be important is making sure that distribution for how we kind of manually and artificially mangle this text. We'll want to make sure that that distribution is similar to what the real thing is like. So that's certainly, challenging. So perhaps, a sort of a maximum entropy perspective is, the way to take on that and kind of make as few assumptions as possible. That way, anyway, that's a question for a more detailed question later on. Anyway, so that's kind of the goal there. So essentially, try to create an ancient Greek autocorrect by taking known documents and then mangling them and trying to recover the unmangled original version. So as far as our vision for the future of AI-assisted digital humanities, um, what we want to do with all of this is to eventually create an application that houses all these AI tools um, that can be used by uh, a non AI expert, which just a simple humanities person, not that they're simple, but just a non AI person in the humanities who has no training in AI or transfer learning or deep learning or ResNets or whatever, and but they know their classics, they know their Greek, and they know their Latin and so on. And essentially, can we give them a tool that has all these things built in that just helps them do their work much faster and increase their throughput and efficiency? So the whole idea is, to kind of improve the efficiency of, these people's work so that we can, get through more than 15% of Oxyrhynchus in 100 years. So as far as, work that's been done for that, we've developed a sort of a little proof of concept application that has the HTR part done. Basically, this little application lets you uh, pass an pass an image into a little web interface, a little JavaScript HTML page. It can run the HDR models on them. It also includes a bit of user interaction where if you notice that certain yellow maybe found a faulty character or it missed one, you can then go in and kind of manually kind of modify a little bit. So kind of a sort of a human in the loop with AI kind of set up there, and it can basically handle that for you. That's cool. Um, and we also have we've been looking into using graph databases and blockchains for kind of managing. Essentially, one of the big problems is that the infrastructure for publishing and managing editions of transcriptions of these ancient documents is kind of outdated. They'll appear kind of just in random journals here and there or on a few websites, and it's not really centralized in a way. Or I shouldn't say centralized. It's not really uh, we'll say centralized in a way that it's everything's in one place and everybody can see everybody's transcriptions of all the fragments. Because if two papyrologists look at the same fragment, they might get slightly different transcriptions. And especially now that we might have AI agents or human in the loop with AI agents publishing these things. It'll be really good to have a kind of a common location where all this stuff is stored. So what we've been looking at is using graph databases and blockchain and smart contracts to try to um, manage the storage and sharing and passing of all these information about these transcriptions. And also, we already have a software called Proteus, which is software that actually allows um, um, papyrologists to basically load up an image and then draft their transcription of it. So the idea is instead of creating an entire thing from scratch, what we would like to do is basically integrate these tools into Proteus this kind of pre-existing software, and essentially kind of build that out and make this kind of enormous, awesome platform that basically everybody in the world can use who works on this kind of problem. So that is essentially our vision for the future of AI in the humanities. A couple more brief things. Beyond ancient Greek and so on, our group is starting to look at a few more things. We've a professor at MTSU who studies actually the Civil War. He has a big collection of Civil War documents that need transcription. Um, we've started working with him a bit, and we're also looking at partnering with believe it or not, the Country Music Hall of Fame because they have a bunch of archives of digital images of things that need metadata. So we're looking at helping them transcribe their stuff. So what we're kind of essentially looking at here is a sort of a larger scope project that aims to create methods for reliable AI transcription of either historical documents or digital documents and so on. And we're looking at obviously some grant funding for that, likely through the NEH or a few other non-governmental agencies. Or agencies are one word, but a few non-governmental entities, we'll say. So that concludes my presentation. I would love to hear questions from y'all, and I'll throw it back to everybody.
Yeah, thank you very much, Dr. West, for the wonderful talk. I have learned a lot from your talk. I know that it's a very challenging problem to solve. I just have a couple of questions, and then we will go with the audience to ask
Hmm.
questions.
Yeah.
My first question is about what do you do when there is an overlap in identifying the characters? Because when you use YOLO, I think I found there are some overlaps between the adjacent characters, right? So
Yeah,
that will
yeah.
affect the accuracy. And my other question is, how do you kind of um, validate these predictions? Because do you have already have a ontology or a database which will already label the data set, or like how do you validate that from the real labels? How do you label your data set?
Yeah,
Yeah.
so let me answer the second one first. So when people when the crowdsourcing effort was done and people said this here is an alpha, right? The cropping algorithm not only actually crops out the character, but it has to figure out the bounding boxes in order to do so. So the bounding boxes are actually stored, and that's how YOLO is transfer learned. So we actually have a big CSV of all the bounding boxes of all the characters, and that's how the actual data set for YOLO is stored and then trained. As far as um, managing duplicates, so for any individual, 640 by 640 image, YOLO tries to handle those itself, but sometimes it doesn't, perfectly. And when it doesn't, we don't currently have a way to handle that. But as far as doing duplicates across multiple kind of sliding window uh, regions, for that we actually do have a way of resolving that. So essentially, imagine uh, you have, alpha, 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 alpha. Imagine you had like this sliding window here,
Mhm.
and then you had this one. So these guys will be found in both of them. We can detect overlaps like that pretty easily, and then we'll essentially just pick one of them. I forget if we pick the one that has the highest Euler confidence or whatnot. But like a year ago, I coded that, and I did a way to pick one or the other. So that part is handled. So when it comes to multiple sliding windows, those overlaps are dealt with. When it comes to a single YOLO image, beyond what YOLO does itself, we don't as of yet have a way to handle those overlaps.
Okay.
I think I got your questions. Is that all?
Yeah, yeah. Just another question on the algorithm. So you have used ResNet only in your experiments. Have you tried any other vision models that could be applicable on this data? Yeah.
Yeah, before I got involved, they tried Tesseract, which is an actual a detection and classification combo, but it really more so works for things like non-cursive things, missing modern things are written like say PDS and so on. So that didn't work very well because of the highly damaged and cursive nature of the Greek. After that, they tried CNNs and then even CNNs with an XG boost layer at the end. That did better. Um, ResNets were then tried, and they were the best out of all those. So we've stuck with ResNets for the individual characters. When it comes to um, using entire cropped patches of characters, we're using actually efficient net for that. I obviously, tried some of the models and determined that efficient net seemed, efficient net B3, I think actually it is. That one seemed to be perform the best per, cost of time to train and so on. So we're using efficient net B3 for that. So we're still using ResNet because
Okay.
go ahead. Sorry.
Okay.
Okay. Yeah, that
Thank you,
works.
Dr. West. Let's go with the audience. I will start with the questions on the chat. We have one. And Dr. West, you also have access to the chat. So if
Hmm.
it's a long one, you can actually read that. So the question is, was there a method used to artificially mangle the known text? That is the Odyssey, for example, using a fragment of papyrus that has already decayed and use that image, the example to test accuracy. Did the team randomly assign distortions to the known transcriptions?
This is a good question. So this is the NLP stuff is the stuff that we've most recently started working on. So we actually don't have any trained models yet, and we're still debating about how we want to handle the artificial mangling. Right now, what we're looking at, essentially, the more assumptions you make about the mangling distribution, the the higher chance your model will have of doing better on that mangled data set because you will mangle it less if you assume that say alphas and deltas they look similar so the model will tend to mix those up. Well, it'll have fewer things to go fix. But in general, is that what's going to happen all the time? So it would be good to make as few assumptions as possible. So we have yet to get to the point where we can really test different mangling strategies and see, okay, um, is a sort of maximum entropy distribution. Um, does it give us the most kind of robust possible outlook of all possible distributions, or is it so general that we actually can't get good accuracy? We're still kind of in the trial and error and discussion phase about how to do that since this is a new phase of the project. So it's a good question. I think what we're eventually going to do is there if you go on say the Berlin or Florence sites for many of their papyri that they have there they have transcriptions of them, not for all of them but for many of them they do. So what we'll eventually get to the point of doing is take our HTR transcription and compare that with it, and then also take our auto-corrected HTR transcription and compare that and see if it was improved. But like I said, we're still at the beginning phase of the NLP part. The HTR and the dating part, that's been going for much longer, so we have much more results and stuff on that. But the NLP is quite new, so I can't really say about that.
Okay. Thank you very much. Another question we have on the chat is super cool project. Just curious, do you translate some of the text into our modern language, especially those in the same line, horizontally, I believe, and any cool words or interpretations? Yeah.
Yeah, we're actually not doing translation. We're doing transcription, which is just essentially copying down what's there. So we're not trying to then translate it into modern English. That's not been one of our tasks yet. It is ancient Greek, not modern Greek. So it would be hard to like I said, there is a kind of a low data, issue with ancient languages. So training something like that can be kind of hard. But as of yet, we're not working on translation, just transcription.
Okay. So we still have time for questions. If any of you have any questions, you can unmute yourself and ask directly with Dr. West.
Dr. West, can you hear me?
Yeah, I
This
can.
is Doji. Yeah, this is Doji. I was looking at the the epsilon transcription on your papyrus. And for me, for your to be as accurate and say that that is an epsilon, have you guys maybe look into kind of like a because when you look at your epsilon, sometimes for me I feel like it might be a foxtrot on the F,
Mhm.
but is it how do you guys want to really accurately find out that is actually an epsilon?
So the the best thing we have is just essentially, obviously you can argmax the distribution, the probability distribution that the ResNet gives you. One thing that you can do is essentially you can look at that distribution and see um, one thing that you can actually calculate is something called the Shannon entropy. If people haven't heard of the Shannon entropy as a measure for measuring uncertainty in a distribution, I would highly recommend it. Essentially, what it looks at is how uncertain or conversely how certain a distribution is. So essentially, if your distribution is really peaked towards one value or a couple of values, it'll have low entropy. If it's really flat, kind of uniform, it'll have high entropy. So a really good measure of how confident a um, a distribution is at its prediction is its entropy. If it's low, that means it's really confident. So essentially, that's kind of what we look at there. When we're filtering out characters, we'll get rid of the ones that have high entropy, aka it has kind of a mixed result. It doesn't really know much. Is it epsilon or is it eta or whatever? It can't really make up its mind. So we look at the entropy as one means of kind of determining how reliable a prediction is. But beyond that, there's not much you can do. I mean, all you have really is basically what the model gives you.
Okay, thank you so much, Dr.
Hmm.
West.
Yeah.
Any other questions from the audience?
No, I think for me, Dr. Graham, great presentation. It was just fascinating to see how we can, bring decades of history back to life and see what, AI application can do in that front. It's really, really fascinating.
Hmm.
My question for you was, I'm just curious, do you guys have any subject expert to be able to look at some of these, writings or whatnot and confirm that it kind of aligns with, obviously you need some sort of decades of research and archive that were stored somewhere to be able to justify that it matches 100% with what you guys are trying to predict here. Can you talk a
Yeah.
little bit about that front?
Yeah, James Purcell's here, associate professor at UK. He is our classicist. He is the guy that is the papyrologist that knows the languages and such. He's really cool though because he also has a lot of CS experience. So he actually does know a lot of AI stuff, but his primary field is classics, and he leads a couple labs and a ton of grants with UK. So he's a really cool guy to have on our team. We also have several other people that we don't work as closely with, but we do a bit. Let me go back over here. When we were working on the paleographic dating stuff, all this, we published a paper that featured a couple of people from the Berlin and Florence archives. They were the ones that suggested that we start using this patch dating, basically uh, add a sort of 25th character that is an entire patch of several lines together that will let you look at inter-character and inter-line features. So having them as well really helps give us some ideas about what to pursue because we wouldn't have thought to do this without them saying, "Hey, you should try that," and then lo and behold, our accuracy is a whole lot better. So it's really really good having some subject matter experts on our team.
Got it. No, thanks for that
Hmm.
clarification. Really impressive. The reason why I'm asking, I think there's also a debate currently with I believe the Mona Lisa, where in Paris they have a different version, and then also I believe in Italy they have a different version. So there's that back and forth in terms of which one is the original and stuff like that. And
Mm.
British also they have a in Britain they have a different version that's so there's that back and forth to prove that the original version started, whatever they believe it started in which country. So to be able to see this technique that you guys are using, I think that could be something to explore further with 2 or 3 different pieces of Mona Lisa artwork and try to trace back the original origin and stuff like that. So yeah, really, really impressive work. Yeah.
Awesome. Thank you. Thanks for your questions. I should mention, as far as student involvement, I'm certainly very interested in working with students. We have a few students from MTSU who are on the project, but it would be good to have a few people here. As far as stuff that one can do on the project, the project it spans quite a range of different tasks and kind of disciplines. So obviously there's the computer vision part with transfer learning and such, with classification and detection and stuff. There's obviously now the NLP stuff. There's character image generation. There's software development and like full stack development for the applications and such. There's even blockchain and database stuff that we're working on. So there's basically we have all the fields on our one project. So if anybody's interested in that, I would love to hear from y'all if y'all want to join, or even if y'all are just interested in more information, just email me and we can have a meeting with the rest of the team and let you know more about it.
Okay. Thank you very much, Dr. West, for the wonderful presentation and talk. And I think it's time for ending this talk today. So you all don't forget to fill out the feedback surveys to improve these seminar talks. And we have the next one on next Thursday, February 20th, from our speaker from Vanderbilt University. You all will get the invites for that. And thank you very much for all of your time, and have a great day. Thank you.
Thank you all.
Bye-bye.
Thank you, Dr. West.
Thanks, Taji.
Yeah, thank you.